All right. So now, yesterday, if you remember the previous section, we learned about a weak acid. So I told you that weak acid, when you dissolve it in water, because it is a weak acid, it is not going to fully dissociate. So if you're taking, let's suppose, 100 molecules of HA, if you're taking, let's suppose, 100 molecules of HA, so definitely what is happening? You tell me. It is going to form H plus and A negative. Yes or no? So out of 100 molecules of HA, let's suppose we have 25 molecules which broke down. Yes or no?
Right.
So when 25 molecules which broke down, so we discovered, we also understood what is the meaning of degree of dissociation. So the degree of dissociation would thereby mean 25 over 100. Yes or no? Isn't it?
Yeah.
So that's the concept. So that's the concept of degree of dissociation. I hope you're understanding. So degree of dissociation means 25 over 100. That means number of particles dissociated. Alpha is equals to what? Number of particles dissociated over the total number of particles. Yes or no? That is
Yeah.
alpha. That is alpha. All right. So I basically told you that alpha percentage. So if you remember, we basically started with all of this part. So we said that if we have 1 mole of HA, so we have 0 moles of H plus and 0 moles of A negative initially. But as the time passes by, so if out of 1, alpha percentage of 1 breaks down. So what is alpha percentage of 1? What is alpha percentage of 1? 1 minus alpha. Isn't it? Because alpha times 1 would be alpha, isn't it? That means what? That 1 minus alpha would thereby be what? 1 minus alpha. So it would be alpha and alpha. But that was when the initial concentration was 1 moles per liter. When the initial concentration was 1 molar, isn't it?
Yeah.
But here, what does it mean? It means C times 1 minus alpha, because normally we do not take 1 molar, we take C moles per liter. You understand? We take C moles per liter. So that shall be C alpha, that shall be C alpha. Are you understanding?
Yes.
So it would mean C times 1 minus alpha into C alpha, C alpha. I hope you're understanding the concept. All right. And we knew that, this is going to be in equilibrium, because obviously, since it is not dissociating fully, that means the forward reaction is not happening fully. The forward reaction is not completing itself. Some reactant is left behind, and some product is also, little bit of product is formed. Are you understanding?
Yeah.
What is the basic concept right here? That means you understand. It means that when I write about the equilibrium, you remember that for equilibrium situations, what do you think we write? We write down the equilibrium constant. And what is the equilibrium constant? That is the concentration of the products, upon the concentrations of the reactants.
Yes.
So what is the concentration of the products? So the reactants is also H2O. So what is the concentration of H plus? It would be C alpha times C alpha over C times 1 minus alpha, isn't it? So it is going to be K equilibrium would be H plus into A negative over HA, the remaining acid at equilibrium, and water. And for this equation, HA plus H2O shall give you what? Shall give you H plus and OH negative. So what do you think we have it right here? Just tell me. When I have K equilibrium, right? When I have K equilibrium, what would that exactly mean? It would sort of mean that, when I have H plus and A negative, H plus was what? 1, 0, 0. From 1, if alpha percentage breaks, then alpha percentage of H plus and alpha percentage of OH negative is formed. So C times 1 minus alpha would thereby form C alpha, isn't it?
Right.
So what exactly do you think here is going to happen? Just tell me. So we have H plus. How much amount of H plus do you think is formed? C alpha. How much amount of A negative? What is A negative here? It is OH negative, isn't it?
Okay. Right.
So
Right.
here it is going to be A negative. So the A negative here is going to be again C alpha, C times alpha.
Yeah.
HA would be C times 1 minus alpha. And H2O would be what? H2O basically is going to be what? It's a constant. Why? Because I always told you that if you take 1 molar, if you take 1 liter of H2O, yes or no? So 1 liter of H2O means 1000 ml of H2O. And the density of H2O is what? 1 gram per ml of H2O. Density means that for every 1 ml H2O, the mass shall be 1 grams. I hope you're understanding. The mass
Yes.
shall be 1 grams. And when the mass shall be 1 grams, what exactly do you think it would mean? Tell me. It would mean 1000 grams. Are you understanding? So that means 1000 ml water was weighing 1000 grams. And when it was weighing 1000 grams, what do you think it exactly means? Tell me. What do you think it exactly means? Tell me. It means 1000 divided by 18 would give me the moles that would turn out to be 55.55 moles. Are you understanding my point?
Yes.
So when we have 55.55 moles of water, and I told you that, at 25 degrees Celsius, the temperature, out of 55.55 moles of water, only 10 raised to power minus 7 moles of water breaks. Yes or no? Only 10 raised to power minus 7 moles of water breaks. I hope you're understanding.
Yeah.
So when only this much amount of water breaks, what exactly do you think would happen? Just tell me. What exactly do you think would happen? 10 raised to power minus 7 moles of water break. So this is a very, very low concentration. 10 raised to power minus 7 is 1 upon 1, 2, 3, 4, 5, 6, 7. And that would mean 0.0000001. This much moles breaks down, isn't it? And this is a very, very small value with regards to 55.55. So if you say that,
Right.
how much is left, how much of water is left, so you would say 55.55 minus 0.0000001. That would amount to 55.5444449, isn't it?
Right. Yes.
And this is a very slight change, For me, for all practical purposes, the concentration of water remains 55.55 moles. Are you understanding my point?
Yeah.
Tell me. Any doubts in this?
No.
What does that mean? You understand. What does that mean? That means if I write down the concentration of water here, for me, H2O is a constant. Okay, H2O is a constant for me. And when H2O is a constant, what exactly does that mean? The constant multiplies into K equilibrium. So that will give me what? K equilibrium times the concentration of water shall be C alpha into C alpha over C 1 minus alpha. So this K equilibrium into water shall be called as Ka. You understand? That K equilibrium into water shall be called as Ka, and you cancel C and C, and you will have C alpha square over 1 minus alpha. Yes or no?
Yeah.
So this is the expression. And this is an expression for what kind of electrolytes, for what kind of acids? For those acids, for those acids which cannot break fully, which are weak acids, which are weak. You understand the point? For those
Yes.
acids which are weak or which
Yeah.
do not dissociate fully, which does not dissociate, which does not dissociate fully.
Okay.
You understand the point? So it is
Yes.
those acids which do not dissociate fully. That's the important point right here. So you see here what exactly is happening. That ma'am, when these acids are not dissociating fully, they are dissociating very, very less in quantity. Their amount of dissociation would be very, very less. So when their amount of dissociation is very, very less, what exactly does that mean? You tell me. What exactly does that mean? That means that ma'am, alpha is very, very less than 1. Okay? Very, very less than 1. That means only, out of 100, only 1% is being broken down, or only 0.01 moles is being broken down out of 100%. So you can very well understand that, out of 100%, if only 0.01 moles breaks down, what do you think from here? Tell me. What do you think from here? That means out of 100, if only 0.001 moles break down, this is a very less value. So in comparison to the original value, this is nothing. So similarly, we say that, if out of one whole, only alpha percentage is broken down, and that too very, very weak acid is there. Extremely weak acid. So for that extremely weak acid, can I say alpha is going to be really, really less than 1? Can I say that? Tell me. Because alpha decides that, how many moles of acid would be broken down. I hope you're understanding. Alpha decides it.
Right.
Alpha decides it. And that alpha is sort of what is very less. I hope you're understanding. This alpha is really very less. Understood or not? So then if you say, if I subtract 100 minus 0.001, that would be 99.999. Don't you think that should approximately be equals to 100% only? Tell me. So if this is my 1 and this is my alpha, and if alpha is really small, don't you think that should also amount to near about 1? Isn't it?
Right.
So my point here is that when we have this kind of, the concentration difference, 1 minus alpha, what exactly does that mean? You understand? That means that, 1 minus alpha is nearly, nearly equals to 1. And I can say Ka shall become C alpha square over 1. So Ka is going to be C alpha square, and thereby alpha square is going to be K over C, Ka over C. And alpha would thereby be Ka by C. Understood or not? Yes or no? That
Right.
would be alpha. Any doubts in this? Okay.
Yeah.
So what exactly does that mean? That, ma'am, alpha means what? Degree of dissociation. So more and more amount of alpha will be decreasing, more and more amount of alpha will be released, okay, if concentration is less.
Okay.
And if concentration is less, what exactly do you understand from this? You tell me. If concentration is less, what do you understand from this? You tell me. That means that, it is more diluted solution. Now I'll tell you one thing. Understand one thing. We have a beaker, right? And we have some amount of water in it and few molecules of sugar, okay? Or some sugar, let's suppose. Let's suppose 2 moles of sugar. Let's suppose 2 moles of sugar, isn't it? Right?
Yes.
Now, what does it mean? What does it mean? It means that, here, what do you think we have? Here, what do you think we have? We have it right here. But I have added more water to this. Like, let's suppose initially the water was, let's suppose, 1 liter. So I had 2 moles of sugar per liter, isn't it? Isn't it? Now, what is happening? Now, what is happening? I have added 1 liters of water extra out from outside. So now it becomes what? 2 liters of water.
Right.
Now it becomes 2 liters of water, isn't it? And when it becomes 2 liters of water, the sugar is still the same. I have not added any extra sugar into this, right? Right? I have not added any extra sugar into this. Sugar is still the same, but water has increased. But water has increased. Now you tell me, will the solution taste equally sweet as it was earlier, or is it is going to taste less sweeter? Tell me. Is it going to taste exactly the same with the same sweetness? Or is it going to taste less sweeter after the addition of even more water from outside? You tell me.
Would be less sweet.
Less sweet. That means it is less concentrated. That
Right.
means it is less concentrated. Less concentrated basically means the taste will not be as sweet. In case of a salt, the taste will not be as salty. In
Yeah.
case of a bitter substance, the bitterness would not be so much bitter.
Right.
My point here is that if you add a lot and lots of water to this, the solute, which is the sugar, will disperse, will scatter in the entire liquid. You understand? And when it will scatter in the entire liquid, what do you think would happen? What do you think would happen? Tell me. What do you think would happen? That, ma'am, the same amount of sugar will now be dispersed. So I would say in 2 liters, now there are 2 moles. Earlier, in 1 liter, there were 2 moles. So thereby, in 1 liter, it would be 2 over 2 moles per liter. And that would be 1 mole per liter. I hope you're understanding. So now the concentration is 1 mole per liter, but the total moles are 2 moles. The total volume is 2 liters. But per liter, only 1 mole is coming because that number of moles are actually sort of dispersing. Are you
Okay.
understanding?
Yeah.
What am I trying to tell you? What am I trying to tell you here? That when we have 2 moles of liter per liter, isn't it? When we have 2 moles per liter, and it is going to be 1 moles per liter. Yes or no? So the more and more amount of water you add, you are sort of diluting the solution. And now, what is the importance of dilution for a weak acid? You understand? When we say that HCl is a strong acid, we say that HCl is a strong acid, okay, and we say that HF is a weak acid. That means HF does not dissociate fully. That means HF does not dissociate fully, but HCl does.
Right.
Now, what is the purpose? What is the reason of why HCl does not dissociate fully and why HF dissociates fully? So, first of all, you have to understand that if you have this beaker, right? If you have this beaker like this, and if you have HCl, and if you have Cl is partially negative and H is partially positive, so you understand that no acid can act as an acid in the dry medium. In the dry medium, isn't it? No acid can act as an acid in the dry medium, isn't it? You will have to have some amount of moisture. You will have to have some amount of moisture, isn't it?
Yes.
So what exactly does that mean? That, ma'am, when you add a water to this acid, only then this acid is going to act as a only then this acid is going to act as a acid, because acid is something which can release H plus ions, isn't it? So, and here the water, what is going to happen? The O negative of it, the O negative of it, that is going to that is going to pull H plus on the other either side. Are you understanding?
Yes.
So this is going to pull here and this is going to pull here, and don't you think this HCl shall break? Definitely. But H is a smaller atom, right? H is a smaller atom.
Yes.
Cl is a bigger atom. And because Cl is a bigger atom, I hope you're understanding that this bond is longer bond. The nucleus to nucleus distance is a longer bond. I hope you're understanding.
Yes. Right.
And when it is a longer bond, you know, when it is a longer bond, I hope you're understanding that this bond shall break very quickly, right? Why so quickly? Because, ma'am, the electrons right here in the center, these two electrons in the center, these two electrons in the center, these two blue electrons. So they are experiencing the force of attraction of the red electrons, the red nucleus, and they are also experiencing the force of attraction of the black nucleus, isn't it?
Yeah.
So what exactly does that mean? You tell me. That ma'am, when this is happening, when when the red nucleus is also experiencing the force of attraction and the red nucleus is also experiencing the force of attraction, do you realize that this bond is sort of going to break very quickly? Because since the bond length is longer, the force of attraction coming from the red nucleus and from the black nucleus is very, very small. I hope you're understanding. Any doubts in this?
No.
An HCl bond thereby will break very quickly because with little bit of, with little bit of pull from the water molecules. With little bit of pull from the water molecules, this HCl bond can break very quickly. So we say that, even if the small amount of water is present, even if a small amount of water, even if small amount of water is present, that is enough to break the bond. Are you understanding my point? Okay. Even if a small amount of water is present, that is enough to break the bond of a of a stronger acids.
Right.
So because an acid, if I'm calling an acid as an acid, a strong acid, there is a reason behind it. That ma'am, the bond is a weaker bond. And because the bond is a weaker bond, are you understanding? So it releases a lot of H plus. And because it releases a lot of H plus on breaking, it is a strong acid. So 90% cases, if you find some acid as a strong acid, if you find some acid releasing a lot of H plus, the reason behind that is the reason behind that is that ma'am, that acid is definitely going to do what? That acid is definitely going to, have a weaker bond. And when that bond quickly breaks in the presence of little bit amount of water, that bond quickly breaks. And I hope if that is happening, you will call that acid as a strong acid.
Right. Okay.
Understood. It's a very important topic because this topic is interrelated to the topic when you come to cells. So if I'm the concept that I'm explaining you right now will help you there. So this is nothing to be neglected. This is a reasoning and this is to be used somewhere. Then we
Right.
have HF. Now let's talk about HF. H is this small atom again. H is this small atom again with the nucleus. And F is this nucleus atom. Are you understanding my point?
Yes.
So when we are talking about HF, okay? So this bond, this electrons here in the center, do you understand that they experience the attraction from H and from F both? Because electrons are negative. You understand? The electrons are negative and the nucleus are positive. So when the nucleus is this nucleus is, positive, the positive attracts the electrons. This red nucleus is positive, so this red nucleus shall attract the negative electrons, isn't it? And this red nucleus, if it is attracting the electrons, so you understand that these electrons in the center, they are being held very, very tightly. I hope you're understanding.
Yes.
They are being held very, very tightly because first of all, it is a shorter bond. And what is the importance of the shorter bond? That this shorter bond will experience the force of attraction is experiencing the force of attraction of the nucleus from very close distances,
Okay.
which is why this bond is a very, very, strong bond. So now we say that it is an acid definitely. So you have a big beaker, you know, you have a big beaker. So when you have this big beaker, what exactly happens? We have HF, we have partial negative, and we have partial positive. And now you put it into water. So water definitely you understand from this point what we are saying. We have HF. You understand?
Yes.
So it is this thing. It is this thing. Are you understanding?
Yeah.
So O carries a negative charge and H carries a positive charge. And we have H plus. I hope you're understanding. What do you think I'm trying to understand? That ma'am, when H plus, pulls H plus of water, they pull F here, and O negative of water will pull H here. Don't you think this bond is going to break? But ma'am, HF is a strong bond. It's a shorter bond, isn't it? HF is a shorter bond.
Yes.
If HF is a shorter bond, what do you think would happen? You tell me. It is a stronger bond. And because it is a stronger bond, because it is a stronger bond, so small, few amount of, less amount of H2O cannot break this bond. I hope you're understanding.
Yes.
So when less amount of H2O, HF, H2O can't break this bond, what exactly do you think would happen? What exactly do you think would happen? Tell me. Tell me. Then ma'am, when we have this HF bond, so I will have to add more and more amount of water because to pull H apart and to pull HF apart, you need a lot of force. Okay? And that lot of force is going to do what? Tell me. That lot of force is going to do what? That lot of force will break it. But to apply that much amount of force, we need lots and lots of water molecule. So only not just, one H, not just one H. We have H and H and O. We have H and H and O. So lots and lots of water molecules will be pulling it apart.
Right.
So, here, if I say for a weaker acid, so if you add little bit of water, if you add little bit of water, isn't it? So that little bit of water, you know, will not be in a situation to do what? That little bit of water will not be in a situation to do what? You tell me. Will not be able to break HF.
Right. At home.
So you need to add more and more water. You need to add dilute it more and more. So the more the dilution, you know, then you assume that, yes, now HF can break. You understand my point?
Yes.
You understand? Now you can assume that HF can break and it can break into more and more ions. So if you keep on diluting and diluting and diluting, what do you think would happen? If you keep on diluting and diluting and diluting, what do you think would happen? That there would come a time that, this HF might break 100%, might break 100%. And this level of dilution, you will not believe. So let's start from here. Let's suppose we have a glass of water.
Okay.
And from that glass of water, I have added 1 mole of HF.
Yeah.
Now, what do? I take a little bigger beaker of water, which has definitely more water than the glass, and I pour entire solution here. So if I had 1 liter of water in the glass, I would have, let's suppose, 3 liters of water in the bowl. Still, HF is not broken down fully because HF1 is really strong. Mole is definitely 1 mole. Are you understanding? Here is going to be what? Tell me. Here it is going to be what? So we have a bigger beaker. We have a tub and we pour the entire mixture here. So you have more water here. Let's suppose it is 10 liters of water. You understand my point?
Yes.
So then what does it mean? Tell me. Then I keep on, neutral. I keep on diluting it. I keep on diluting it. Yes or no? So then what do you think would mean? I have this. So it would be, let's suppose, 100 liters of water. I take a bigger tub and then I finally transfer it to a swimming pool. Then you assume in the swimming pool it might dissociate fully. You understand? So do you realize the extent of dilution HF would need to break 100 into 100?
Yeah. Okay.
Why is that happening? Because ma'am, to pull one HFs apart, lots and lots of water molecules are needed, and 3 liter or even 10 liters or even 100 liters water
Yeah.
will not be
Yeah.
sufficient to break it.
Right.
So
Right.
this is called infinite dilution. This is called infinite dilution.
Okay.
So when you infinitely dilute any liquid, any weak acid, only then you assume 100% dissociation. Otherwise, it will either be 50% diluted or 20% diluted, or even at 10, 15, 30, 40 liters also, it is just
Yeah.
1 to 3%, 1 to 5% diluted. This is very, very less level of dilution. I hope you're understanding.
Right. Yeah.
What I'm trying to tell you is that, this is alpha, and this is a very, very less alpha. This is alpha, and this is very less alpha. I hope you're understanding the concept that I'm trying to explain you. Any doubts in this? Just tell me.
No,
Okay,
I got it. Yeah.
right? So when I call some acid as a weak acid, when I call some acid as a weak acid, what do you think it means? A weak acid is a weak acid whose bond is strong. Can I say that? Whose bond is strong. And HCl, if I call some acid as a strong acid, that means it is giving me a lot of H plus because its bonds are weak. Are you understanding?
Yes.
Okay. So first thing, this is important. And because of that, because the bonds are weak, so even less quantity of water, even less water, even less water is enough to break the bond, is enough to break the bond.
Okay.
And HF, when we talk about HF, so even more water, no matter how much amount of water you add, is can't break the bond effectively.
Okay.
Can't break the bond effectively. You understand the point?
Yes, ma'am.
Okay. Now, so for weak acids, there would never be full dissociation and they will always use an equilibrium sign.
Yeah.
But for the strong acids, there would be a single arrow which indicates the completion of dissociation. That if you
Okay.
have added 100 HCl, the 100 HCl shall break down. If you are taking, partial HF, right? So then you will have
Yeah.
strong bonds are there, less strong bonds are there. I
Right.
hope you understand the concept.
Yes, ma'am. I do.
Okay. This is the concept. So it says even more H2O can't break the bond. This is very, very important concept to understand. And now
Yeah.
you see how we calculate the pH of such solutions. Just see. It says you have
Ma'am,
okay. So now in HF, since you see this equilibrium sign, so I hope you understand that every equilibrium has an equilibrium constant.
yes.
And
Yeah.
I am not writing down water here, but definitely you understand water has to be here. Okay. Water has to be here. Are you
Okay.
understanding the point?
Yeah.
Okay. So when we are talking about water, so with every weak acid, so first of all, nobody will tell me that, this is a weak acid or this is a strong acid.
Okay.
I will have to figure it out on my own. The best way and the easiest way to figure out whether this acid is a weak acid or whether this acid is a strong acid is by the sign of the equation. If you see this double sided arrow, this clearly indicates it is a weak acid. You understand? Why? Because only a weak acid can have an equilibrium established in it.
Okay.
Because
Right.
only then this is possible that, the two ions want to combine back to form HF. Okay. But if I'm writing down some acid like this, then that means that it is a strong acid because it is dissociating up till completion. Are you understanding? It is
Yeah.
dissociating up till completion. So that is the concept. That, just have a look at the arrow, and that arrow will indicate, that what kind of acid it is, whether it is a strong acid or whether it is a weak acid. Do you understand the point?
Yeah.
Oh. What exactly do you think we have it right here? Just see. When we talk about this, right? So for every equilibrium, we have an equilibrium constant. So the question will also give me Ka. Ka is, let's suppose, 1.8 into 10 raised to power minus 5. This is called as the dissociation constant of an acid. This is called as the dissociation constant of an acid. Okay? Dissociation constant of an acid. You understand the point?
Yeah.
So when we talk about the dissociation constant of an acid, This value, first of all, understand one thing. If this value is very high, what is this dissociation constant? Because it is an equilibrium constant only. But it has been given a special name as the dissociation constant of an acid. I hope you're understanding. You understand? So when I say Ka shall be H plus into F negative over HF. Isn't it? That's product over reactant, because every equilibrium constant is like, every equilibrium constant is what? Tell me. It is product concentration over the reactants concentration. Are you understanding? So you tell me that, if I have to write down Ka, if I have to understand that, what does high Ka mean? High Ka means the value of Ka would increase when? Because ma'am, Ka is a ratio. Ka is a ratio of whom? You tell me. Ka is a ratio for whom? It is a ratio of product over reactant.
Yes.
And this is sort of a fraction. And every fraction increases when the reactant is high and the numerator is less. You know, if I reduce the denominator, it's like here. If I reduce the denominator, this is my denominator and this is my numerator.
Yes.
So my numerator is high and my numerator denominator is less. You understand? So basically, when my denominator is very less, it keeps on decreasing and decreasing and decreasing. And if the numerator goes on increasing and increasing and increasing, then the value of Ka shall increase. Are you understanding? When do you think the numerator would increase? Tell me. When do you think the numerator would increase? Tell me. The numerator would increase when the numerator would increase when, you know, the products HF would increase. And when would HF would increase? Tell me. When the reaction will move in the forward direction, isn't it? When the reaction shall move in the forward direction. I hope you're understanding.
Yes.
What I'm trying to tell you here is that, ma'am, when this is happening and if the reaction, the acid dissociates more and more, then the acid releases more and more amount of H plus. And when the acid releases more and more amount of H plus, then the reactant here, when then the product here increases. And when the product increases, that product is written down in the numerator. So my numerator is also increasing. And if more and more HF has been broken down, then very less amount of HF is left. And when very less amount of HF is left, what exactly does that mean? You tell me. When very less amount of HF is left, what exactly does that mean? Tell me. That, ma'am, that HF left is here written in the denominator. That means that is very less. So don't you think that fraction shall sort of increase because the denominator is decreasing and the numerator is increasing if the acid is dissociating a lot? Tell me. If the acid is dissociating a lot, the value of Ka shall increase. Are you understanding?
Yeah.
And
Full.
if the value of Ka is increasing, what exactly does that mean? Tell me. When the value of Ka is increasing, what exactly does that mean? Tell me. Tell me. It means what? It means what? It means that, if the value of Ka is high, it indicates a strong acid. It indicates a strong acid. And if the value of Ka is less, that means, ma'am, HF has not dissociated fully. Isn't it? HF has not dissociated fully. Are you understanding? And
Yeah.
when HF has not dissociated fully, that means H plus and F negative has not been formed in good quantity. And when H plus and F negative has not been formed in good quantity, what exactly does that mean? You tell me. When H plus and F negative has not been formed in good quantity, what exactly does that mean? You tell me. That, ma'am, lot of HF is left behind, undecomposed, and very few H plus and very few F negative ions are formed. And this product is written here in the numerator. And this HF is written in the denominator. Yes or no? That means what? That means what? That, ma'am, the value of Ka is less because the numerator is less and the denominator is very, very high.
Right. Yeah.
And lesser value of Ka indicates weak acid. Are you understanding? So if one question that generally comes at, they would give you the value of Ka. It says there are two acids. It says there are two acids. One whose Ka is 1.8 into 10 raised to the minus 5, Ka1, and another one whose Ka2 would be 1.8 into 10 raised to power minus 7. Which acid do you think would be a stronger acid? Acid 1 or acid 2? Tell me. Which acid do you think would be a stronger acid? Tell me.
One would be the strongest.
Ka1, definitely, because Ka2 is lesser. 10 raised to
Yeah.
minus 7 is lesser. So then by looking at the value of Ka only, I can indicate, which is a stronger acid and which is a weaker acid. So this is one type of question that they would first give you. So just to identify the strength of the acid, which is a stronger acid and which is a weaker acid. I hope you're understanding the concept.
Right.
So this is one part. Second part that you see here is this. So when we are talking about this particular part, so understand when we say that there's an acid, let's suppose HF. Now real question basically starts here. It says if I have HF, and HF sort of breaks like this: H plus and F negative. Yes or no? So they have given me the Ka for this acid, which is the dissociation constant of an acid, which is 1.8 into 10 raised to power minus 5. And they have given me zero point 0.1 molar HF. All right. Now the question tells me calculate the H plus ion concentration, calculate the F negative ion concentration, calculate the OH negative ion concentration, calculate the HF ion concentration. Question tells me calculate the pH. Matlab, anything out of these they could ask you. And they're all related, okay? There is only one method to solve these kind of questions.
Right.
So you have to proceed in such a manner. What would you do? So you will have zero point 0.1 molar HF, isn't it? So when you have zero point 0.1 molar HF, okay, so H would be 0 and F would be 0, isn't it? H would be 0 and F would be 0. So from zero point 0.1 molar minus alpha, so H plus would be alpha and F negative would be alpha, isn't it?
Yeah.
Because alpha percentage of it is broken down. So my concern here is I will not be taking alpha. I would be taking simply X. I would be taking simply X. So what would X mean? I will say X moles out of zero point 0.1 moles, because zero point 0.1 mole per liter is given to me. That means when they were preparing the solution, they added zero point 0.1 moles of HF in 1 liters of solution. I hope you're understanding. So basically what is happening, they're going to mix zero point 0.1 out of zero point 0.1 moles totality. Only X moles, let's suppose they dissociate. So if X moles dissociate, do you understand that zero point 0.1 minus X moles remain there itself?
Yeah.
Are you understanding? And thereby X moles of H plus would be formed and X moles of F would be formed out of zero point 0.1. So what is X here? X is representing the number of moles of HF which got dissociated, which got dissociated, okay, from zero point 0.1. Simple. Very simple. Are you understanding the concept?
Yeah.
So now I am going to write down the equilibrium constant, because the equilibrium constant, so that should always be the second step. No thinking about it. This chapter is not tough. You have to remember the standardized steps. The
Okay.
concentration would be given to you. Initially, the product shall be 0, 0. Out of zero point 0.1 moles, if X gets dissociated, so accordingly, X moles of H plus and X moles of F negative would be formed. So you will be left with zero point 0.1 minus X moles of HF. Then
Okay.
you substitute the values. So x you put in here, this x you put in here, because obviously f negative is here, and 0.1 minus x you substitute here. So Ka here shall be x into x over 0.1 minus x. And that value is 1.8 into 10 raised to power minus 5. Yes or no? And you look at the value, this 10 raised to power minus 5 is really, really less, very less. So what you can do? You can neglect this x. You can neglect this x. And when you can neglect this x, it would become x square over 0.1. And that would be 1.8 into 10 raised to power minus 5. Are you understanding the concept?
Yeah.
And now, how easy do you think? Because Ka value was given to me, so I have just substituted the value. So don't you think x square shall become 1.8 into 10 raised to the minus 5 into 0.1? Understood or not? Tell me.
Yes. Understood.
Okay. And if I solve this, I get 1.8 into 10 raised to the power minus 6 under root. So I will have 10 raised to the power minus 3 into under root of 1.8. And if I calculate x, 1.8 into 10 raised to the power minus 3, okay, do you realize what is going to happen? Just tell me. If I say that, x is going to be 1.8 into 10 raised to the minus 3, okay, what is that? What is that according to you? Tell me. Under root of this. So you have actually figured out what is h plus, because h plus is nothing but x. And
Right.
then
Yeah.
x you have figured out. You've also figured out what is f. If you know h plus, can you not calculate OH negative? If you can calculate OH negative, can you not calculate pH? Can you not calculate POH?
Yeah. We
Yes
can
or no?
calculate a lot. Yeah.
And we cannot, can we not calculate F negative? We can calculate all of these. So we will
Right.
be doing in the next class, right? But up till now, I hope you understand this X finding X method.
Yeah.
And these are
I,
the standard steps, okay? For this chapter, if you remember these steps would be common to all the questions that you take into account.
okay.
Okay, so this much you need to remember. Then no matter what they ask, we will discuss about this in the next class.
Okay, ma'am.
All right?
Got it.
All right. Thank you.